Okay, this is Indira, Assistant Professor of Institute of Aeronautical Engineering, Department of Mathematics. Today we are going to refer the last unit of linear algebra and calculus, that is Fourier series. Fourier series is one of the important topic of expressing the any function in terms of infinite expansions. Fourier series, which is named after the French mathematician Jean-Baptiste in 1768 to 1830, and Fourier series is an infinite series representing the periodic functions. Mostly, the periodic functions are used by the Fourier series to expand in the infinite series. It is a very powerful method to solve ordinary and partial differential equations, particularly with periodic functions appearing as non-homogeneous terms. We know that the Taylor series expansion is valid only for functions which are continuous and differentiable. And Fourier series is possible not only for the continuous but also for the periodic functions and functions with continuous and the functions which are discontinuous in their values and derivatives because of the periodic nature. Fourier series constructed for one period and is valid for all. So let us see how to expand any function by using the Fourier series and to what period, what type of Fourier coefficients exist. Now, before going to how to expand a function with the help of the Fourier series, we need to know what do you mean by the periodic function. A function which gives same values after regular intervals of time is called as a period. And that interval with which it is given again and again the same value is called as a period. A function f raises from R to capital R, that is real numbers to real numbers, is said to be periodic if there exists a positive in number t such that f of x plus t is equal to f of x for all x belongs to the real numbers. And here t is called as a period of f of x. We need to stress the definition of this periodic function because we are using only the periodic functions to express in the infinite terms by using the Fourier tools. Now, for example, sin x and cos x is a periodic function with a period 2 pi. Sin nx and cos nx is a periodic function with a period 2 pi by n. Similarly, tan x is a periodic function with a primitive period pi. Tan nx is a periodic function with a primitive period pi by n. If f of x is a constant and is a periodic function, but it has no primitive periods. Now let us see what is the definition of the Fourier series. According to the definition of the Fourier series, a function f of x defined in the interval 0 to 2 pi, where f of x is a periodic function, that means f of x plus 2 pi is equal to f of x. Then Fourier series is given by f of x is equal to a0 by 2 plus summation n raises from 1 to infinity an cos nx plus bn sin nx. Here a0, an, bn are called Fourier coefficients and they are given by the formula a0 is equal to 1 by n integral 0 to 2 pi f of x dx, and an is equal to 1 by n integral 0 to 2 pi f of x cos nx dx, and bn is equal to 1 by pi integral 0 to 2 pi f of x sin nx dx. And these values an, bn and c and a0 are called as a Fourier coefficients of f of x in the interval 0 to 2 pi. Not only in this interval 0 to 2 pi, for any interval it is they are considered as a Fourier coefficients, but first we are considering the interval 0 to 2 pi to expand any function in terms of the Fourier series. So what we need to do is to find out the three Fourier coefficients and substitute in f of x formula to get the Fourier expansion. Okay, so what we need to take the function, substitute in the a0 formula and an and bn value formula, try to get all the three coefficients, resubstitute in the main formula to get the Fourier series of the given expansion. So that is the main aim of this module. So let us see with one example. Find the Fourier series of the expansion f of x is equal to x square, x raises from 0 to 2 pi, Hence, deduce that 1 by n, 1 by 1 square plus 1 by 2 square plus 1 by 3 square, so on up till infinity is equal to pi square by 6. Similarly, 1 by 1 square minus 1 by 2 square plus 1 by 3 square, so on up till infinity is equal to pi square by 12. Similarly, 1 by 1 square plus 1 by 3 square plus 1 by 5 square, so on up till infinity is equal to pi square by 8. And all these three are the deductions which are done after getting the Fourier expansion of the given function, that is f of x is equal to x square. So let us start the solution for finding out the expansion of f of x is equal to x square using Fourier series. Now, the given what is given f of x is equal to x square. Now a naught is equal to 1 by pi integral 0 to 2 pi x square dx. Integral of x square is x cube by 3. We are following that integral of x to the power of n is equal to x to the power of n plus 1 by n plus 1. So by using that formula, I could able to get the integral of x square is equal to x cube by 3. And now you substitute the upper and the lower limit. Upper limit is 2 pi and the lower limit is 0. So wherever x is there, you substitute upper limit x, that is 2 pi. So that becomes 8 pi cube. 8 pi cube by 3 into 1 by pi, and pi gets cancelled, leaving 8 pi square by 3 is the a naught value which we got the first value. So keep it aside. This is the first value we got, the first Fourier coefficient a naught, that is 8 pi square by 3. Now let us go for the second Fourier coefficient. Second Fourier coefficient a naught is equal to 1 by pi integral 0 to 2 pi f of x cos nx dx. There is a difference of cos nx from a naught to an. The function has to be multiplied with cos nx, and then we have to integrate it within the limit 0 to 2 pi. So integrals x square cos nx is the required integral that we need to get, and after getting the integral value we have to substitute the limit. And for this, the best formula that we are going to use is integral of f into g, and which can be expressed as f dash, okay, g1 plus f into g1 minus f dash into g2 minus plus oscillating series f double dash into g3, so on, which is an oscillating series where f double dash refers the first, second and third derivatives, so on, for the function f, and g1, g2, g3 indicates a single integral, double integral, triple integral of the g value, so on. So here g is nothing but cos nx, g is nothing but cos nx, and x square we refer it as sin nx. Vice versa we can't do, because if you interchange it, if you assume that x square is equal to x square is equal to g and cos nx is equal to f, then the integration goes on up till the infinity. We can't do. So always f, the function, the product of the function, from the product, always we should take the the function which has the limited derivatives, so that the integral can be done within 2 or 3 steps. So here x square is as it is, integral of cos nx is sin nx by n minus derivative of x square, that is 2x, minus integral of sin nx by n, that is minus cos nx by n square, already n is there, multiply again with 1 by n, which gives 1 by n square, plus 2 into minus sin nx by n cube from 0 to 2 pi. Now you substitute the limits. So if you substitute the limits here, say at the upper limit and lower limit, the first product will completely goes to 0. Even the third product also goes to 0. So only you are left out with the 2x cos nx by n square. So wherever x is there, the upper limit is 2 pi. You substitute cos n into 2 pi. So which is nothing but 4 pi by n square. So pi here, the outside 1 pi, and the inner the numerator pi will get cancelled, leaving 4 by n square. This is the an value, the second Fourier coefficient that we had find it out. Now still one more coefficient is there to find out. Then we have to substitute in the expansion, the Fourier series to get the infinite expansion. So let us see the last Fourier coefficients Bn, how to get the last Fourier coefficient. Bn can be given by 1 by pi integral 0 to 2 pi f of x sin nx dx. That is nothing but 1 by pi integral 0 to 2 pi x square sine nx dx. Again, you follow the same formula, that is integral of f into g, f into g1 minus f dash into g2 plus f double dash into g3, so on. So it comes out to be 1 by pi x square minus cos nx by n minus 2x into minus sine nx by n square plus 2 into cos nx by n cube from 0 to 2 pi. Now, we have to substitute the upper and the lower limit. The middle term will completely vanishes because at the upper limit 2 pi sine n pi, sine x becomes 0 and the lower limit 0, sine x becomes 0. So the middle term completely becomes 0 and we need to substitute, we'll get the values in the first and the third term. So which comes out to be 1 by pi minus 4 pi by n square plus 0 plus 2 by n cube minus 0 plus 0 plus 2 by n cube, and which is nothing but minus 4 pi by n is a bn value. So all the three values are ready with us, and now we need to substitute all the three values in the Fourier expansion. F of x is equal to a naught by 2 plus summation n raises from 1 to infinity a n cos nx plus bn sin nx, which comes out to be 1 by pi 8 pi square by 3 plus summation n raises from 1 to infinity 4 minus 4 by n square cos nx minus 4 pi by n sin nx. Now, we'll take all the values of x n raises from 1 to infinity. So the first term here 2, the numerator 8 and denominator 2, it goes in 4 times. So 4 pi by 4 pi square by 3 plus 4 into cos nx by 1 square plus cos 2x by 2 square plus cos 3x by 3 square, so on, minus 4 pi into sin x by 1 plus sin 2x by 2 plus sin 3x by 3 plus so on, and put x is equal to, now this is the required expansion. Now we are left out to get the deductions. There are 3 deductions asked in the question, that is 1 by the summation of 1 by 1 square plus 1 by 2 square, so on up till is equal to pi square by 6. Similarly, the oscillating series and the addition of the all odd numbers 1 by 1 square. So for this deduction, we have to make use of the expansion that we have got it. That is, this is the expansion. In this expansion, you try to put x is equal to 0. If you put x is equal to 0, then f of 0 is equal to 4 pi square by 3 plus 4 into 1 by 1 square plus 1 by 2 square plus 1 by 3 square, so on, so on so forth, minus 4 pi into 0. But x is equal to 0 is a point of discontinuity. So we have f of 0 is equal to f of 0 plus f of 2 pi by 2, and which is equal to 0 plus 4 pi square by 2, and which comes out to be 2 pi square. So therefore f of 0 is equal to 2 pi square. So let us see further. Now you substitute left hand side, wherever f of 0 is there, you substitute 2 pi square. So 2 pi square is equal to 4 pi square by 3 plus 4 into 1 by 1 square plus 1 by 2 square plus 1 by 3 square, so on. And bring this 4 pi by pi square by 3 on the other side. So we are going to get it as 2 pi square minus 4 pi square by 3 is equal to 4 into 1 by 1 square plus 1 by 2 square plus 1 by 3 square, so on. And this comes out to be, after taking LCM, 6 pi square minus 4 pi square, that is nothing but 2 pi square by 3 is equal to 4 into the term which is there in the inside bracket, that is 1 by 1 square plus 1 by 2 square plus 1 by 3 square. Now we bring this 4 on the other side, so you are going to get the first deduction as 1 by 1 square plus 1 by 2 square plus 1 by 3 square, so on, is a value pi square by 6. Still we need to get 2 more deductions. Once again we'll use the formula, that expansion. In the expansion, now we'll substitute in, instead of x is equal to 0, we'll substitute x is equal to pi. These are the assumptions that we need to do in order to get the deductions from the expansions that we have got through Fourier series. So pi square is equal to, because x is square. So if we put x is equal to pi, we will get it as pi square. Pi square is equal to 4 pi square by 3 plus 4 into minus 1 by 1 square plus 1 by 2 square minus 1 by 3 square. Take minus as common here and bring this 4 pi square on the other side. So you are going to get minus pi square by 3 is equal to minus 4 into the oscillating series 1 by 1 square minus 1 by 2 square plus so on. So therefore, if you bring this 4 on the other side and the negative term is get cancelling, so we are going to get it as 1 by 1 square minus 1 by 2 square plus 1 by 3 square. So on till infinity is nothing but pi square by 2, which is nothing but the second deduction of the equation. Similarly, we need to get the third deduction. The third deduction can be easily brought by just adding 2 and 3 equations. So the first equation, the second is nothing but the equation that we have got from first deduction. Third equation is nothing but the equation that we have got from second deduction. So try to add these two deductions. So the first, the LHS is added and RHS to RHS is added. So pi square by 6 plus pi square by 12 is equal to 2 into 1 by 1 square plus 1 by 3 square plus 1 by 5 square, so on. And after taking LCM, we'll be getting 3 pi square by 12, which is equal to 2 into 1 by 1 square plus 1 by 3 square plus 1 by 5 square, so on. So pi square by 8, 3 goes in 4 times, and for 2, it is brought again to the denominator to get pi square by 8, and which is equal to 1 by 1 square plus 1 by 3 square plus 1 by 5 square. So this is how we can able to get even the third deduction also. So I'll recapitulate once again. Fourier series is a tool to expand any function in the given interval. Mostly the function should be a periodic function in order to apply the Fourier series. That is a must and should. The periodic function is nothing but the function which gives the same value again and again at the regular intervals of time, and the interval within which it is giving the same value is said to be the period. So the mostly if suppose f of 2n plus x is equal to f of x, then 2n is nothing but the period there. So like that we'll call it as, right? So in this Fourier series, we need to find out the the Fourier's expansion, that is f of x is equal to a0 by 2 plus summation n raises from 1 to infinity an cos nx plus bn sin nx. And we need to find out the 3 Fourier coefficients a0, an and bn. So these 3 coefficients bears the formula as 1 by pi integral 0 to 2 pi f of x dx, and an is equal to 1 by pi integral 0 to 2 pi f of x cos nx dx. Similarly, bn is equal to 1 by pi 0 to 2 pi f of x instead of cos, we will refer here as sin nx dx. So after finding out the 3 Fourier coefficients, we need to substitute in the Fourier expansion to get the regular expansion of the given function in the given interval. So that is how we can apply the Fourier series. And here we have referred with an example with 3 deductions. F of x is equal to x square. I've used the same expansion formula. I found that the 3 Fourier coefficients. A0 I got it as 8 pi square by 3, and an I got it as 4 by n square, and bn I got it as minus 4 pi by n. Substituting all these 3, we'll get the Fourier expansion. Now, going to the deductions. For the deductions, we have to assume the x values, not only for this question, even in any other question, deductions are brought by assuming the x value. So here I have assumed x is equal to 0 to get the first deduction, and x is equal to pi for the second deduction, and simply added 1 and 2 to get the third deduction value. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.